Thank you for joining us for integrating spatial data with CO2 measurements. Our speaker is Eric Price, Applications Associate for LI-COR.
Thanks, Ashley. My name is Eric Price. I've been with LI-COR for about 1.5 years in technical support, and I've been involved with the testing and implementation of the GPS and CO2 integration.
Thanks, Eric. So also joining us today are several panelists. Let's go ahead and let them introduce themselves.
I'm Jason Hupp, Applications Analyst here at LI-COR.
Rod Madsen, Product Manager.
All right, I'd like to thank our panelists for taking the time to be with us today as well. So let's turn the floor over to our speaker.
Thanks, Ashley. Today's webinar topic is integrating spatial data with CO2 measurements. Before we get into today's webinar, I'd like to point out that LI-COR has several other resources for CO2 measurements. We've got a series of webinars based on the soil CO2 flux measurements that includes some of the theory, the techniques, the advantages of automated measurements, and what you can do to ensure quality data when measuring soil CO2 flux. You can view these webinars at the link at the bottom of the screen. Before we begin with today's webinar, we'd like to ask a poll question. Ashley, can you bring that up?
All right, Eric. Let me get that popped up on our screen for our audience. It looks like today's question is, how often do you use global positioning data in your research? And the answers are, I have not used it before. I have used it a few times. It plays a significant role, or it is a vital part of my research. So go ahead and click the radio button next to your choice, and we'll give everyone just a few moments to submit an answer.
All right, thank you for participating. It's interesting to see how many of you use GPS data on a regular basis for your research. In this webinar, we'll be talking about the advantages of incorporating GPS data with CO2 measurements. We'll discuss the methods of measurement, both the accumulation chamber method for measuring soil CO2 fluxes, and the continuous method for measuring ambient CO2 concentrations. Then we'll point out a few applications where CO2 mapping can be very useful, and we'll finish up with a few hardware considerations. So why would we want to incorporate GPS data into CO2 measurements? Well, the simple answer is that CO2 flux rates and ambient CO2 concentrations vary from place to place. Some areas act as sources, releasing CO2 from the ground, and other areas act as sinks, taking in carbon dioxide. The prevalence and magnitude of local CO2 sources and sinks depends on factors such as biological activity, such as respiration, soil properties, such as porosity and organic matter, and environmental variables, such as temperature, moisture, and air pressure. In addition, anthropogenic sources such as vehicle emissions also play a large role. Soil CO2 flux or ambient CO2 concentration can be combined with latitude and longitude to provide better insight into the location and nature of these sources and sinks. A widely accepted method for chamber CO2 measurements is to measure the carbon dioxide coming out of the soil in a chamber measurement. An accumulation chamber is placed over a soil collar, which is placed in the ground. A pump draws air from the chamber into the CO2 analyzer and back in a closed-loop method. Over time, the CO2 concentration in the chamber increases and eventually reaches saturation. The CO2 flux can then be calculated using a linear or exponential fit. The soil collars must be inserted into the soil a few days or even maybe a few hours before the measurements are taken. These provide a simple way to take quick measurements without disturbing the soil, which would disturb the CO2 flux. When recording positioning data along with CO2 data, it's important to consider the spacing of the soil collars. If the collars are placed too close together, positional errors might affect the interpretation of the results. In this example, GPS plotted points are placed on the left, and on the right we can see the actual grid of soil collars. Even though the collars were spaced 10 meters apart, the GPS accuracy was only within 3 meters, and so there's a perceptible difference between the two plots. This is an important consideration for collar placement. A chamber measurement can begin a few days or hours after the collars have been positioned. After configuration, the system can be carried out into the field to begin chamber measurements. The chamber is placed over a collar, and typically the measurement only takes a few minutes. The LI-8100A Automated Soil CO2 Flux Analyzer, shown here, enables these measurements to be automated, meaning that you can have a consistent observation length and also adequate mixing within the chamber for each measurement. Once measurements are finished, the results should be examined to ensure quality data. You can watch our webinar entitled Quality Assurance and Quality Control of Soil CO2 Flux Datasets for more information. You can find it at the link at the bottom of the screen. Since latitude and longitude were recorded along with each chamber measurement, the results can be plotted in a false color image in plotting software such as SigmaPlot. The map can also provide more details. In this case, we plotted CO2 fluxes as the false color image, and then soil temperature is overlaid on the screen. These measurements were taken with an LI-8100A CO2 analyzer, which enables carbon dioxide, soil temperature, soil moisture, and GPS data to be logged concurrently, along with many other variables. The image on the previous slide can also be imported into Google Earth and overlaid on the map. This provides an excellent way of visualizing the differences in CO2 flux across a landscape. These observations were taken over the span of a few weeks using an LI-8100A automated soil CO2 flux analyzer with a survey chamber and a GPS receiver. These several measurements can be viewed as a time series to further examine these environmental processes. So we're looking at a series of chamber measurements in Lincoln, Nebraska on the edge of a forest. CO2 flux is shown as a false color image, while average soil moisture and temperature are also displayed at the bottom there. These observations, like I said, were taken over a few weeks, and we can see soil moisture, temperature, and CO2 flux varied greatly amongst the 25 collars and over the span of the different days. As you can see, the soil flux, for example, increased dramatically after several rain events. CO2 concentration measurements can also benefit from additional spatial data. A CO2 analyzer can sample the air continuously across a transect, across the landscape. Instead of a soil chamber, an intake tube is attached to the analyzer. This is a less quantitative method of identifying CO2 flux rates, but it allows for sampling of a much larger area than survey chamber measurements. An important consideration for these measurements is the intake height. A plume of CO2 emanating from the ground might dissipate not far from the ground. So in this example, CO2 was released from a point source from the ground at a rate of about 2 liters per minute. The red and yellow indicates a higher than usual concentration of CO2. but it was not easily detected at above 30 meters or 30 centimeters above the ground. Although this was a low flow rate, not a typical example, it's still advisable to consider intake height when you're starting your continuous measurements. So continuous measurements are intended to cover large areas, so the analyzer should be portable. The analyzer can be mounted on a vehicle or even carried by hand. And when you're carrying it by hand, we recommend that you attach the intake tube to a meter wheel or some other device so that you can keep the intake height consistent above the ground. Once the measurement's finished, the continuous data should be examined to ensure quality control. These measurements will typically be displayed as rows in a text file. As you can see, you've got water vapor, carbon dioxide, temperature, latitude, and longitude all in the same row. An excellent way to quickly visualize the data is to plot it in Google Earth. LI-COR provides a program that converts the text file generated from the LI-8100A in continuous mode into a KML file, which can be opened in Google Earth. In this example data set, the elevation is analogous to the CO2 concentration, so it looks somewhat like a bar graph. With measurements taken every second, this data was generated by walking around Lincoln, Nebraska with an LI-8100A analyzer and an integrated GPS receiver. We're recording carbon dioxide, latitude, and longitude once per second. Here we can clearly see differences in CO2 concentration. The lowest concentrations are around 350 parts per million, but the larger spikes that you can see, those are around 1,200 parts per million, and those are the results of diesel equipment at a construction site. With measurements taken every second, you can see even minute differences. On the right, we were coming through a quiet bike trail, and then you can see the spike on the left once we hit a busy street. The large peak you see here, that is carbon dioxide pooling underneath a train overpass. So just to recap, there are two types of measurements that can benefit from GPS data. You've got chamber measurements, which are measuring the soil CO2 flux using a chamber placed over a soil collar. And you can also do continuous measurements where you sample the air and record ambient CO2 concentrations. Before we proceed, I'd like to ask another poll question. Ashley, can you bring that up for us? All right, thank you for participating. It's good to see what our customers are using their instruments for. So both of these methods, the chamber method and the continuous method, can be used in a variety of applications. In addition to the typical soil CO2 flux chamber measurements, there are several fields where CO2 and GPS data logged simultaneously can be very beneficial. One of these is urban ecology. It's the study of ecosystems within cities or other developed areas, and it usually involves the comparison between urban and natural environments. It's a rapidly growing field because of the growing interest in the relationship between anthropogenic emissions and the quality of living, standards of living. Carbon dioxide forms a primary component of these emissions, both from vehicles and industrial sites. Cities are often characterized by a higher ambient concentration of CO2, also known as a CO2 dome. Large variations exist even within this dome. Carbon dioxide concentration can be a possible indicator of air quality, so making urban ecology and environmental studies a vital field. Variations in concentration within cities and in comparison with rural areas can be mapped with high resolution using the continuous measurement method. Often the analyzer is loaded into a vehicle which is driven around inside the city. For example, the spike in concentration that you see here happened when the vehicle carrying the analyzer entered the downtown area of Lincoln, Nebraska. Volcano research could also benefit from the integration of GPS and CO2 data. Volcanology places a particular emphasis on predicting volcanic eruptions because of the often catastrophic results. Underground volcanic activity releases CO2, sometimes in deadly quantities. It has been hypothesized that soil CO2 flux could possibly play a role in predicting volcanic eruption. And if this is the case, plotting and monitoring CO2 sources could play a tremendous role in volcanology. Scientists have already shown that mapping CO2 fluxes or with concentration measurements can provide useful information about a volcanically active site. Carbon capture and sequestration is probably the newest application that could benefit from these types of measurements. Carbon dioxide released by power plants and other industrial facilities. Carbon dioxide is collected, pressurized, and injected underground into geologic formations, usually emptied oil reservoirs. Ideally, this carbon would remain underground for thousands of years, effectively offsetting or at least reducing CO2 emissions into the atmosphere. For this reason, sequestration fields must be monitored to make sure the CO2 doesn't leak out of the reservoirs and re-enters the atmosphere. Several protocols are in place to monitor for leaks from the rock to the soil to the surface to the atmosphere. These are some of the examples of well-established methods that can be used for assurance monitoring. You can see reservoir pressure measurements check the movement of CO2 injected throughout the rock. And then at the surface, isotope analysis, eddy covariance, and vegetation response are all used in conjunction with soil CO2 flux to make sure that unusual amounts of carbon dioxide aren't seeping through the soil. Both chamber and continuous measurements can be used for assurance monitoring. Continuous measurements could scan large areas of the site for leaks and quickly identifying any leak sites. If a potential leak is found, chamber measurements could more accurately identify and quantify the CO2 flux rates. In 2010, LI-COR tested the combination of chamber and continuous measurements through the Zero Emissions Research and Technology collaboration in Bozeman, Montana. Every year, researchers are invited to test their monitoring technologies against a controlled subsurface CO2 release. Here we can see the false color image of soil CO2 flux from chamber measurements at that site. You can see on the left there's little variation in flux rates before the release, but on the right, however, the injection site is clearly seen after or even during the CO2 release. Continuous measurements taken around the same time confirm this observation. The concentrations on the left are fairly homogeneous, and that's before the release. And then during the release, you can see on the right there are high spikes in CO2 concentration, and these match up with the high flux rates observed. using both of these methods to scan sequestration sites for leaks can add just another level of assurance. So there are a few requirements in order to make these measurements, and the LI-8100A Automated Soil CO2 Flux Analyzer meets all of these requirements in one easy-to-use instrument. It features an infrared CO2 and H2O analyzer, an internal pump, internal data storage, and some processing. It's portable and it's rugged. And it also includes chamber automation for use with LI-COR soil chambers. And now there is the possibility for a GPS receiver to be attached to the analyzer. The new 8100-405 CO2 Mapping Kit enables the analyzer to log GPS data as well. It includes a Garmin GPS receiver, a mounting bracket, an intake tube for continuous measurements, and an additional cable for use with LI-COR chambers. The GPS receiver sends data to the analyzer for both survey and continuous measurements, providing a useful tool for integrating spatial data with CO2 measurements. All right, this concludes today's webinar. Ashley, do we have any questions from the audience?
Yeah, Eric, I passed most of them along to our panelists. However, I did save just a couple for you to do live. The first one is, what is the accuracy of the GPS unit that LI-COR sells?
Thanks. That's an excellent question. The Garmin GPS receiver that we sell with the 8100-405 mapping kit, it's accurate to within 15 meters worldwide. However, in North America, we've got the Wide Area Augmentation System, known as WAAS, and that enables the receiver to be accurate to within 3 meters, I believe.
All right, thank you. The next question I have is, does LI-COR provide any software to plot CO2 with GPS data?
That's a good question as well. LI-COR doesn't provide any software to plot the data on a grid. However, we do supply some supporting software. So the 8100A comes with file viewer software. So you can examine chamber data, you can recalculate fluxes if necessary, and it also allows you to export the flux and other variables to a text file, so that you can use it with your plotting software of choice. For continuous measurements, the 8100A outputs data in a CSV file, so you can put that into almost any plotting software as well. We also provide a CSV to KML converter, which will take that file and put it into something that Google Earth can use.
Great, thank you, Eric. That's really all the time that we have for questions right now. I hope everyone's questions were answered. If by chance you haven't received an answer, just stick around. Our panelists are still working on the questions that you've submitted. If you'd like to continue your conversation with the panelist, you can do so offline via email or phone. Just go ahead and give your information to this panelist you've been speaking with. I'd also like to inform you that an on-demand replay of this presentation will be posted to our website soon. So watch your email or visit www.licor.com/env/webinars for more information on how to access that. Thank you for joining us today, and we hope to see you at our next webinar.